Uh, Professor Hales has joined the OSU faculty in 1998. He's a seagoing oceanographer who builds the instrumentation and analytical tools he uses to infer ocean processes that control the carbon cycle. He spent nearly 2 years at sea on over 15 different vessels and over 25 ports of call in all the major ocean basins of the global ocean. Burke joined PacWave team as chief scientist in 2017, and he's focused on bringing the grid-connected test facility into full operation. Anyhow, I give you Professor Burke Hales. Thank you.
Thank you. Does everybody hear me okay?
Mm-hmm.
Excellent. All right, well, thanks for the opportunity to present. I recognize a couple of the names there, and we're always happy to give updates and background on the project. I have a lot of slides, and many of them are fairly illustrative. They're show and tell kinds of slides, so I might go a little fast. Make sure to stop me. Use the raise hand function, or just unmute yourself and blurt out questions if I'm going too fast. Okay, so I want to tell you about PacWave and what it is, and maybe as importantly, what it isn't. It's important to know that we're a test facility, and we're not building the devices that make the energy ourselves. We're the playing field where the folks who do that work can come test their devices. Okay, so why wave energy? Wave energy has the potential to provide somewhere between 10 and 20% of US electricity demands. And since we're a grid dependent infrastructure, coastal energy is effectively continental energy as well. Certainly it's regional energy. And where you have a lot of potential power is obviously on the coast, but up here you've got very high wave energy off the US West Coast, particularly off Oregon. And the nice thing about wave energy in comparison to some of the other renewables is it's very steady. The waves don't stop when the sun goes down. They don't go away when the wind stops blowing. You can have nice calm days at the coast and there are still waves coming to the shore. And so we like to think of it as a piece of the energy portfolio, much like your stock portfolio, where this is the guaranteed interest. Even if it's low interest, it's an important part of your portfolio in the context of other resources that might be more spiky, and even if it's not the greatest part. So if we're going to have a portfolio that includes renewables such as wind, such as solar, even hydro, wave is a nice steady backbone resource for that regard. So why Oregon? Well, we're really in great shape in a lot of ways. We have probably the best wave energy resource in the lower 48, and it's the most accessible. I don't know how many of you have spent time driving up the Olympic Peninsula and the Washington coast. Much less infrastructure along that coastline, much less access, fewer ports. And so we've got a robust electrical transmission system, a grid right there next to the coast. We've got good port infrastructure, good transportation infrastructure, and we've got a very established, shipbuilding and manufacturing chain industry in the coast. And what's more, this effort started way before I got involved with a very concerted effort to work with the community to determine best locations, to determine stakeholder concerns and considerations. And so we've been fortunate to have had this interaction with the coastal community and have very supportive environment. One of the first things we hear from people who try and do other ocean infrastructure projects is, how did you get past the community? And our answer is, we started working with them about 10 years ago. And the actual test site was chosen by the Newport fishing community. And on top of that, we've got leading research institutions here primarily Oregon State, but also Portland State, and we've got affiliations with University of Washington, University of Alaska that help us work on these problems. So historically, we've been doing this, and I'm using we very generously to myself. I wasn't doing this since the early 2000s, but Oregon State has been doing this. There's been tens, now exceeding $100 million of R&D, research and development funding, primarily from DOE, but not exclusively. There are a number of wave energy production companies that came out of OSU, and the intellectual property that was generated at OSU, C-Power, Harmonics, 3M Wave. We've done a couple of the, exclusive to us within the continental US wave energy deployments. At our north site, NWI and Azura were the companies that worked there. Lots and lots of PhD and master's students that have come out of these programs. And these students are actively hired by the industry, but also the national labs and other academic institutions. Many different projects and 20 device and research organizations testing at PacWave. It's interesting that coastal stakeholders seem to be quite supportive of wave energy. Maybe not quite as supportive as solar or wind, but much more supportive of geothermal or hydro power. And with strong support for expanding wave energy production. And another kind of fascinating piece about this is that wave doesn't seem to have the political polarization that some of the others do. Now, this may be that wave is new and folks haven't taken entrenched positions about this, but it's pretty clear that there's a smaller separation between self-identified liberal and self-identified conservative respondents to this poll for wave energy, where it's much more it's much stronger for solar and wind, and even reverses, for example, for hydro, where there's more conservative support for hydro than there is for liberal. But wave feels like we're in a pretty good spot where we're broadly supportive and we don't seem to be falling victim to political polarization. Okay, so how do you do it? And, this is, we're in a formative state, and that's really important to think. I won't, I'm teaching right now. This is, I think with maybe the exception of Katie, I might be the youngest person in the audience here. This isn't typically the case for me. But I can remember in the early days of wind energy that the different types of devices and turbines were highly variable. There were, vertical turbines that looked like, streamers, and there were, many vaned windmills. There were enclosed turbine style approaches. There were, hooked blades in these devices, and you'd see them out, randomly in places where somebody was taking a risk to try this. And now if you drive, into the gorge, into Eastern Oregon, and you see the huge wind farms there, every single one of those devices is almost exactly the same. And if any of you have been lucky enough to go to Maui and see their big wind farm installation sort of across the bay from Kihei, big wind farm, they're exactly the same. And the reason that those devices are all the same is because they've had 20 or 30 years of testing and optimization. Whereas if you look at these wave energy devices, it's a hodgepodge of wildly different things, and they're almost in some cases cartoonish. These devices here have a float at the top, and they're like a hinged door that goes back and forth with the waves. You can see back here behind the device. Can folks see my cursor? No. Let me see if I can.
It's on the orange object. No?
I'm trying to get a. Oh, there's a tool here. So my cursor right now is on this in the upper left. Can you see that?
Mm-hmm.
Yes.
Okay. So this back here is a piston. Whoops. And the wave device flops back and forth and activates a piston that actually drives a hydraulic pump and provides hydraulic power. This device, the orange one, has these segments that move relative to each other. The Centricity device is one that's based on a rotating pendulum. This device over here, middle on the left, is actually a turbine. This is the outlet of a turbine here, and I'm sure conceptually this works with waves coming into a volume and compressing air and forcing it through a turbine. I'm sure many, if not all of you, have been to Devil's Punch Bowl, right? Mm-hmm. So there's an opening that faces the ocean at Devil's Punch Bowl. The waves roll into there, and they compress that air into the opening of that sea cave and force it out the top. And someone were to put a turbine in that outlet point, that would be much like what this device does right here, is that the waves surge in and out of the interior of this device, force out air out through here. This device is has got a horizontal pendulum. This one, these floats actually move up and down with the waves, so they look like big feet that get pushed up and down, and they drive generators and or hydraulic systems back here at the shoreline. This is a great example of a shore-mounted device, whereas most of the rest of these are anchored and out in the open ocean. We've got names for them that I don't necessarily find that informative: a point absorber, an attenuator, an oscillating surge wave converter, an oscillating water column, rotating mass, etc. And so there's many different ideas about how to capture this energy, and a big piece of this is because no one's really been able to do detailed testing and optimization. We anticipate that some of these devices and some of these approaches might just not work, but we don't know that because there hasn't been this rigorous testing. Right, so here's an oscillating wave surge device, which is kind of like the one that we showed here. This one as well. This is a device made by a company called Resolute Marine. They've done some testing up at the Navy facility up near Astoria. Submerged pressure differential, as the waves go back and forth or sequentially over a device, the pressure field changes, and so you can drive pistons up and down like this. These are membrane driven, sort of like the opposite of a membrane pump that I'm sure you've all had some experience with. Point absorber might be the easiest one to think about. This is almost like an upside down yo-yo, right? And so the waves move this device up and down, and it's on a tether. And here inside, there's a flywheel or a winch that is rotated and spun as it moves up and down. Yeah, Jean, I see your hand up.
Thank you. Just as we go through some of these, I'm hoping that you will touch on, I was in the legislature from 2007 to 13 when we were mostly focused on wind, but certainly in ocean devices. And especially from the stakeholders' perspective, the concern was whether any of these would actually survive in open ocean in the difficult weather conditions that we have. And then also, how much they would be seen from the shore as far as view sheds and that kind of thing. So I'm just kind of wondering about the testing on their stability and if they should fail or go away or something, the requirements for recovering the device itself.
Yeah, so in my opinion, being a seagoing person and a pretty avid participant in, pursuit of fish and crab in the coastal ocean here, I'm highly sensitive to how abusive the ocean can be. And in my mind, that's one of the really important aspects of this test facility, is that the seaworthiness of these devices is critical. And there are many ways that you can project the performance of these things. There's all sorts of modeling, the same sort of shipbuilding programs that will tell you about hull construction and strength. Those all go into this modeling of the the energetics of the wave field, you know, thoughts about materials, corrosion, et cetera. There are model programs about anchoring systems that you know, tell you exactly what the types of tethers and anchors you need to keep these things from moving away. There are scaled test facilities right here at Oregon State. The Hinsdale Wave Research Laboratory is out on the southwest corner of campus, and so you can build a, you know, 1 to 100 scale device and bring it to the test facility to simulate tests. None of those are the same as being in the ocean. And that's a really, really critical part of what's happening here, is to determine seaworthiness. As far as the, we call it the demobilization, every potential user that comes in here will carry a, you know, a bond that will effectively pay for the, you know, the recovery of those devices. And so that's a requirement for anybody to work with this, is that they can provide some high level of assurance that we actually, you know, won't be left with a new Carissa or something like that. As far as viewscape, the site where these large devices will be is 7 miles offshore at its closest. And there is really no, there's no reason for any of these devices to have a high vertical profile. The energy is generated at the water surface, putting mass up high, just like any of you who might have, you know, tried to pull a fifth wheel across the river in a windstorm, you know, at Biggs or something. You know, that high center of gravity is bad news for anybody, and so that certainly is something that goes into this. And so, you know, you can't, and I'm assuming there are no flat earthers in the audience, so I don't want to offend anyone's sensitivities. You can't see over the horizon, and so if you're at, you know, the elevation of Highway 101, the furthest you can see out to sea, even if your eyes are that good, is 3 miles. And so the only way you could ever see one of these devices would be if you were up high and had really good optics, and at which point it would look like, you know, a vessel, a boat out there on the ocean. So no, we don't think there's a viewscape issue, and there really would be no reason for a device to have such a thing.
Thank you.
Sure. Let's see. Rotating pendulums. This device actually was in the water off of Scotland for 2 or 3 years, and it had this asymmetric flywheel essentially. And so as this device rotated, you'd build up this harmonic rotation of this flywheel, and that would run a generator. This is a picture of it off of Orkney Island in Scotland. This is the oscillating water column device. So as the waves approach, the interior water level rises and falls, and that compresses air. This device right here, I'm going to show you it in the shipyard up in Portland, and it looks like this horrendously big device, but almost all of this device is under the water. And so this comes back to your viewscape question. Here it is right here, right? So they haven't put the turbine on, but basically everything that's not yellow will be underwater. And so this opening here, that's the water column where the wave oscillation drives the pressure fluctuations. And up here is where that turbine is mounted for the compressed air to push through. And this is at, well, you see on the big gantry crane, this is at the Vigor shipyards in Portland, Northwest Portland. All the devices I've showed you so far are sort of focused on grid scale power generation, but there are lots and lots of other reasons to generate wave power, and we call these maritime markets that are effectively smaller scale, isolated power systems, and they can do a number of things like, you know, recharging underwater vehicles, desalinization, aids to navigation, ocean monitoring. One of the big things that's happened recently is that a bunch of the big data companies, Microsoft, Google, et cetera, are thinking about, you know, how do we how do we protect these big data repositories, and how do we, you know, keep them cool? Putting them underwater is one of their ideas. And so these big devices that sit out, you know, 100 feet below the water surface or something like that, they've got energy requirements, and the maintenance is really important for that. Aquaculture, supporting offshore aquaculture facilities. You could consider, you know, making fresh water, generating hydraulic pressure to do algae cleaning, mitigation. You could actually make ice with these devices. Constructed waterways, you can use devices to actually generate I've lost the word, dredging effectively. So hydraulic dredging. So you direct flow, you know, a place like Port Orford, for example, where they spend a lot of money on dredging. If you had wave powered devices that could generate, you know, a discharge flow oriented out of the harbor, you'd maybe not have to do this. Potentially extracting resources from seawater, shoreline protection. We spend a huge amount of money building breakwaters, whose entire purpose is to take the energy out of waves. And we take all that energy out of the waves to protect the harbors and their entrances, but we harvest none of that energy. So it's energy dissipation that's happening, but it's happening in terms of effectively mechanical destruction as opposed to energy capture. Let's see, I think I showed you this slide already. We've been doing this for a long time and doing it with a lot of effect, or a lot of effectiveness. And we're associated with a number of test facilities within Oregon State. The Wallace Energy Systems Research Facility is where there's a huge amount of testing done on the actual power generation aspects of this. And in this laboratory, which is on campus here in Corvallis, they've actually built devices that simulate wave oscillation to which you can connect your power generation systems. There's the Hinsdale Wave Research Laboratory. I'm sure you've seen on Oregon Field Guide the simulations of the M9 tsunami, and they've built mock-ups of the little towns. And basically, you know, in some ways it's the kind of things we did when we were little kids. You know, you built models and then performed destructive testing. And that's often what they do at Hinsdale. And so they've learned a lot about the best practices for construction in the face of a tsunami. And I'm sure you've all seen the new Marine Studies Initiative building. Many of those thoughts and how to construct that building in a way that effectively the lower floors will flood through, but the building will stand, and there are escape avenues to get up above the waterline. Many of those thoughts came from the Hinsdale facility. Autonomous device testing. This is an actual test that happened at our north site, which is about 3 miles off Yaquina Head. And then this connected testing with this horribly oversimplified cartoon that has caused lots of misconceptions about what the system is going to look like. We're building that right now. I'll try and do a better job. I think many of you have probably seen this figure over here on the, I've lost my mouse now.
Burke,
over here on the right.
Don't make fun of my cartoon, Burke. You know.
Well, you know, I've had to defend. There were lots of people who took this cartoon as though it were a 2-scale literal representation. And they said, boy, those things are really right there on the beach. And so yeah, so this is a schematic, and I'll show you with some more realistic scale and where we are in the construction about what it's more likely to look like. Yeah, Katie, I did a talk at Yachats, and somebody went to this picture and said, "You're stealing all the waves. We won't have waves at the beach anymore because of your devices."
I do remember at the time I had this discussion with Dr. Batten when Mark and I did this, but the problem is to show how far it was from shore. It was like the graphic was going to be like super long, so it just didn't work.
We had in response to the viewscape questions, which we field a lot of, somebody said, well, why don't you take a picture of the Oceanus when it's out there? So you go to the beach and take a picture of the Oceanus when it's out there on site, so people will know what it looks like. And of course, it looks like nothing because you can't see it. so it's really hard to impart this scale and the sense of perspective. Okay, so what is PacWave? We are globally significant and recognized. It's an open ocean wave energy test facility, and the purpose is to provide wave energy converter clients. Now, clients is very broad. This could be university researchers, it could be nonprofit, it could be corporations, companies who actually anticipate a business model of selling electricity that come from these devices. But we've got clients that we're supporting and giving them the opportunity to optimize their devices to increase energy capture. Second bullet here, my oceanographer's heart, I kind of wish this was the first bullet, to improve survivability and reliability. Seaworthiness is just a huge, huge issue here. And, the marriage maybe isn't the right word, but the marriage between the energy generation folks and the shipbuilder folks is probably not as close as it could be. It's really going to be important to build devices that can survive, and I think we all know, how destructive the Oregon coast can be. Walking the sidewalk from, up to from England's down into the actual waterfront, and the long list of lost mariners from Newport. I mean, we all know about this. It's very important, just how you get these things out there, how you deploy them, how you anchor them, how you maintain them, how you bring them back in. Those are really critical tests that need to be done before these become widespread. Collect the information about how your power, generating power on the device is not easy, but it's only part of the process. You have to then transport it, transmit it all the way back to shore, condition it into a form that can actually be put onto the local grid. And we need to be able to quantify that and do that in an unbiased and accreditable, validatable way. We need to know how things behave once we get out there. Do we in fact have negative environmental effects? There's no expectation that there will be no environmental effects. We don't know how negative they're going to be. We don't think they'll make a lot of noise, but we've got a very, very extensive monitoring program to make sure that we're not changing the soundscape, particularly in the context of migrating marine mammals in this area. We think they're probably very likely to attract fish. Is that a good thing or is that a bad thing? Are we introducing, artificial reef-like structures in an area where they don't typically exist? I can guarantee you there's almost no lingcod at this site, and there are going to be some when we start putting these anchors down. So we've got a huge monitoring responsibility to just quantify these effects. Okay, so we have two sites. We have PacWave North, which is in state waters. It's about 3 miles off of Yaquina Head. If you were to walk up to Yaquina Head and a device were out there, you could see it. And that's where the tests have happened before. And then we've got the south site, which is just about due west of the airport. That's this bigger rectangle down here. And it's 7 miles from the beach to the inshore edge of this site. And this is the one we're trying to build right now, that we're in the middle of constructing. Basically, all of this from OSU has been funded by the Department of Energy. There's been some support from the U.S. Navy for building autonomous power and production and storage systems. But if you were to look at the dollar percentage, it's almost entirely DOE, with significant contributions from the state of Oregon, Oregon State University, a couple of private foundations and donors. So focusing on PacWave South, which is the one that is under construction right now. It's, again, as we said, the inshore edge is 7 miles offshore in a straight line. We're west-southwest of Newport, about 10 miles. Within this test facility, we'll have 4 separate test berths, each with their own subsea power and data cable. each cable capable of carrying up to 5 megawatts of electrical power. So ultimately, potentially a total of 20 megawatts of power production, and we're permitted for up to 20 devices. These big devices would essentially, you know, you could get maybe 4 of the really big devices in there, but there's a lot of discussion about whether or not a single big device is the best way to go, or if several smaller devices that can capture smaller wave energy and that are networked together. You sort of think of it as a swarm of bees as opposed to, one big angry seagull or something. And so 20 total devices, 20 total megawatts. The cable that run from that site are landing right here at the Driftwood Beach State Recreation Area. And that's where we've been working since July 1st of 2021. And then ultimately we'll grab those subsea cables, convert them to terrestrial cables and run them up to our actual shoreside power conditioning facility, which we call the UCMF, which is the acronym for Utility Connection and Monitoring Facility. Ultimately, from the UCMF, that power will be converted to and conditioned to a format compatible with the Central Lincoln PUD grid, and we will, ultimately be putting some power back onto the grid when this system is functional and we've got devices in the water. I talked about funding support. It's primarily the U.S. Department of Energy, but with a number of other contributors to the tune of 20 or 25% of the total. So where are we? Well, this puts you into the Wayback Machines. Anybody remember 2019? Things were different, but even before then, starting in 2011, OSU folks led primarily, well, at that time, Katie, was Belinda lead or was this Bob that was on point?
What year?
2011?
2011 was Bob, I believe, and then Belinda was shortly thereafter.
Yeah, so started by, even if we go back before 2011, a faculty member here, Annette Von Juan, was the real instigator of wave energy research at OSU. Bob Pash took over as the lead of the Pacific Marine Energy Center, and then handed the reins off to Belinda Batten, who certainly by 2012 was on point here. Katie worked very closely with the team early on here, and did a number of feasibility studies, preliminary designs, application for research lease to BOEM, the Bureau of Ocean Energy Management. Is that right? I want to say there was a mineral in there. Ocean energy and mineral. Anyway, we, based on this work, chose to go with what we call the alternate FERC licensing process. Yeah, is there a question there? I heard somebody break my monologue, but I don't see a hand up. So lots and lots of planning and stakeholder consultation. Ultimately, we submitted the draft of the FERC, that stands for Federal Energy Regulatory Commission. That's where we submitted our license application. The license application is a document that is about 1,500 pages, includes collaborative work with a dozen federal and state agencies, maybe twice that. We've got plans for impacts on bats. We've got plans for impacts on fish attraction. We've got plans for impacts on whales. We've got plans for impacts on the seafloor, crabs, et cetera. Plans for decommissioning and demobilization. All of those went into this document that essentially the draft went out, and then they came back to us and said, well, you've been doing this for 6 years. We need you to do it for another couple of years. And we've submitted our final application in early 2019. And then things got weird. We finally were issued our license in early 21. But we knew that by August of 20, that effectively everything had been approved, but it was going to the desks of political appointees and dying. And we had to spend a huge amount of time trying to figure out who was holding it up where, and who could talk to the right staffer, the right aide to try and get this thing moving. And we ultimately got essentially the authorization to pursue our BOEM lease in like right before Inauguration Day in 21. And so it became really political. I think even though this was a long process in here and there was a lot of back and forth, I think it was good faith and science driven, but suddenly things got weird here, and it just took a really, really long time for us to knock that loose and ultimately get our lease. We anticipated when we submitted the lease, the final application in early 2019, that we'd be starting construction in early 2020. And that didn't come through for us. So we started construction in summer of 21, and I'll show you some details about that. And here we are now in early 22, and so we're basically well into the construction piece of this, probably the most hands-on and high-risk piece of the construction we've effectively just completed. And we're moving on to some others, hoping to be finished with construction in fall of 23 and receiving clients and starting operations in early summer of 24. The lease that we have from FERC is a 25-year license. As somebody said in a meeting, that by the time we get out to the 25-year end of the lease, we hope we all have at the very least different phone numbers. But that's the duration of the lease, and that's the timeline on which we have to project the final decommissioning of the facility. Ruth?
Yeah, I've just wondered, do you have, are there customers lined up who are asking to test there now?
Yeah. We do, and there was actually, again, this is all very formative and it's very subsidized by the Department of Energy. You probably saw that announcement about the $25 million DOE award, and that was awarded to clients specifically to come to test at Packwave South. And so we do. There are a lot, as you might expect, a lot of questions about how we work with these clients, what the contracts are like, how we get supported to actually assist with these folks, and whether or not that comes from the developer or directly from the Department of Energy. There are a lot of things to work out in the next year and 3 months or so. Linda, I just saw your chat question. Yeah, the fishing industry helped choose this site. That rectangle was sufficiently avoidable by traffic coming in and out of Newport, and was in an area that the commercial fishermen did not view as high priority for protection. I'm sure that there are crabs there. I'm sure there's the transient halibut now and then, but it's not an area that's really sought after by the local fishermen for the high dollar fisheries. And so, yeah, that was fine. Fishermen involved in natural energy. Katie, is that the right acronym there? And with a lot of leadership from Terry Thompson and Anno Husing, is that right? Early on in helping
actually, Anna wasn't very involved in that. It was Terry as a commissioner and myself really that took lead. And, I wouldn't say that the area isn't of high value. I don't think that's accurate. I would say that,
right.
I would say it is of high value, but it was an area that they felt met the requirements of the site, because there was some specific requirements that Packwave needed, like a certain type of bottom habitat and that kind of stuff. And they felt like it was the best spot they could find that wasn't as impactful to them as other spots would be, that still met the requirements. So it was kind of a trade-off there. And I think the other thing happening at the same time, which is important to have context on, is while I was leading the effort to have this conversation in Oregon around where is this test site going to go. The territorial sea plan amendment was also going through at the same time inside Oregon's territorial waters to look at where to put sites for marine renewable energy as well.
Right.
And so there was the potential for multiple areas to kind of be given or be, you know, put aside for this. And I think not just the fishermen involved in Natural Energy Committee, but the community, because we had a community siting team as well, not just fine. We had a community siting team. They really felt like they didn't want commercial development at the time. They really felt like the economy of Newport is around testing and research. And so they wanted that testing and research site. So they were, I think, willing to kind of give it up, because they also felt like then maybe they'd be a little bit protected from the territorial sea plan process if they had said yes to this and they wanted more.
Yeah, that's true. We should also point out Bob Etter certainly played a really constructive role in this process. We don't want to forget him, and probably a number of folks that I have forgotten. Let's see. Jean, I see your hand up, but Linda had a question in there. So Linda, I'll try and answer this one. When you say how many acres in the park, are you talking about the offshore area or
the land area?
So the Driftwood Park itself,
yes.
Effectively, we have moved in. I'm sure you've seen the sign saying the park is closed. We've occupied the entire parking lot, and when we're done, we'll have recreational access restored to the park by May 31st of this year. And the only thing you should be able to see of our presence is 4 manhole covers and an improved ADA access ramp to the restrooms. So we're on the hook to basically reconstruct the entire park. Jean, I see your hand up there.
I just wanted to comment that Katie does deserve a great deal of credit for keeping the folks that were necessary to be there at the table, and she supplied a lot of pie to keep the fishermen there.
I did bring a lot of pie. It's one thing that virtual meetings with our fine group is we can't have pie.
Yeah, well, and you know, right when I started was one of the last fine meetings that we had. You know, those fishermen, they have other things to do than sit around and meet with us, and they're a hard group to grab, particularly when you're talking in the fall when they're getting ready for crab season. And so I came to one fine meeting where I went and bought the pies, and I'm disappointed because I'm a pie maker and I'm a snob about pies, and we've never had an opportunity to have a meeting where I can actually provide homemade pie. So Katie, if that's motivation, or you know, maybe they don't trust my homemade pie.
That's pretty good motivation. Belinda used to do that. I have never done that for the fine group. I always bought them, but yeah, let's do it.
All right. So let's see. Let's move on. So yeah, so here we are in early 22. We're well into the construction. We hope to be wrapped up with construction by the end of summer 23, so that we've got sort of 6 months for what we call burn-in. Testing the cables, making sure the facility is operational in the shoreside facility, and then operations in 2024. Okay, so where are we? Well, the permitting's done. We finally got the full execution of the BOEM lease on February 16th of 21, even though we got the news that it was going to happen on January 19th of 21. We got the FERC license finally issued on March 1st of 2021 with a construction authorization date of May 18th. We started construction, moved trucks in, started clearing out the parking lot on the 1st of June, and then really got going with doing the underground construction on the 1st of July. Pictures here. Folks can remember the median between the parking spaces at Driftwood. That's us digging it up. The big Driftwood burl that was there, we saved. Oregon State Parks has that somewhere. We hear it's coming back when the park is put back together, but probably not in the middle of the parking lot. We did a number of things to minimize the effects of construction at the park, both on the neighbors and on the wildlife. And what you can see here is they're building the sound barrier, which is effectively a ring of 40-foot containers stacked too high around the park, so that we were not disruptive to the neighbors or to particularly bird life, nesting birds on the beach. We were very very protective of the snowy plovers that will sometimes nest on the beach and are presumed to be, sound disturbed. Although, those guys are persistent. They'll nest in highly human trafficked areas. That's the wrong word. I'm sorry. High traffic areas. And I'm told that they actually like disturbed beach. So if somebody's been out there, like at Pacific City, driving on the beach and their tire ruts, that the plovers like those because it gives them a little bit of relief to hide from gulls and things that like to rob their nests. We ended up not having any plovers. A couple showed up and visited the neighborhood and decided they'd build elsewhere. But there's a lot of efforts made to sort of minimize our footprint. The construction overview. Here's the site out here off the airport. Here's Driftwood Park. Here's our upland site here. What we're just wrapping up is this, we call it HDD, which stands for horizontal directional drilling. And that's work where we started at the park and drilled 4 conduits out under the seafloor that outcropped at about the 50-foot depth here. Drilled tunnels, pushed conduits in, and we just wrapped up this yellow line here that goes between the park and up to our upland site, which is down south of Seal Rock. We hope to be started building this upland site, this UCMF, starting this summer. We hope to have requests for bids out in a month or two, and awards made by June, and hopefully contracts in place by July, so that we can get started on this construction. Next summer, we've got the subsea cables coming in. And this is a highly specialized operation. There are basically no vessels on the US West Coast that can do this work. And so we're dependent on a vessel that's going to come through the Gulf of Mexico and out through the Panama Canal and up to our coast to do this cable laying work. And hopefully, as we said before, hopefully we're doing grid connected testing by the summer of 24. So that's the sort of big picture timeline. Where we are now is we're just wrapping up this underground construction. And so starting here at the park, we drilled 4 underground bores. They got as deep as 150 feet below the seafloor. Well, we drilled underneath here. Each one of these, prior to doing this work, would have been a record for the length of what they call a shore landing. Each one of these is a little over a mile long. And they outcrop right out here, like we said, just beyond what would be considered the surf line. One of the other pieces about this that's really critically important is that driftwood coincides with one of the few gaps in the shallow rocky reef system that's off the coast there, that many of you have spent time out there. Really great rockfish and lingcod fishing habitat. We didn't want to disrupt that. It's challenging to work in that area. And so this is one of the reasons why driftwood was chosen. So these outcrop here, sort of in an opening between the rocky reef systems, and ultimately the cables will be installed in these conduits and laid out seaward to the test site. This part here, we just finished up this drilling here. We went underneath the park property to the south of the parking lot. Sorry, I don't want to do that yet. And this was a choice that we made because we felt it was lowest environmental risk. One of the earlier plans that we had was to trench out the access road under Highway 101 and then along Highway 101 to the south, and then up the access road to our property here at Wenger Lane. Lots of challenges here. If we're doing it this way in the first place, we would trench across several of the creeks that feed this wetland. Also, very, very dense utilities in that margin along Highway 101. And I'm sure you all love when you get construction on Highway 101, and this would likely happen in the summertime when traffic is the most excellent. And so this underground drilling was viewed as, was a little more costly to the project, but it was viewed as less environmentally risky and less human disruptive than the trenching along the highway. This is what the site looked like. Here's our container wall around the site. You can see cranes in here. They're starting to install the drilling rigs. This little container right here is actually an office trailer. And so the folks that were on site there used this as their office. They had, one of the best view offices on the Oregon coast. And we, those of us sitting here in the valley reminded them of that all the time. So that was, and this was a neighbor who of the construction site who said, "Hey, I got a whole bunch of really nice drone shots of your site." And so I don't know his name, unfortunately. He should get credited for this photograph. But it was really nice to have this aerial view of the operation. This is what it looked like. We had 2 drilling rigs going at the same time. These drill rigs are almost exactly the same as you would bring in for a well drilling operation, but rather than being simply vertical, they go diagonally and horizontally. And they've got, which to me, I think the industry does this all the time, and they're not as amazed as I am, but they have amazing steering capability. So they're drilling underground and they're a mile out, and at some points, over 100 feet below the seafloor. And when they broke through the seafloor, they hit their targets to within a few feet. I mean, it was really amazing that they've got that kind of control and precision. In each hole, we put a mile of steel conduit with special anti-corrosion coating, very specialized terminal ends that have check valves and burst discs on them so that they would stay dry when we installed them, and they will stay sealed until we open them up to pull the sea cables in. This, it's not as dramatic as if you had been there, but this was the moment where we punched through the seafloor to complete the final seaward bore. You can see we didn't manage to finish in nice summer weather. Things were getting a little windy and rainy and muddy there at the construction site. But this is when we finished those bores and then started pushing the conduits in. You can see the pipe here. Pushed them in until they broke out through the seafloor, cut off the extending ends here at the park, and sealed them up. And so these are waiting for us to build the vault where the cables will be connected and installed, and that's actually starting to happen right now. That vault construction. When we did the terrestrial bore, we could go from both ends, right? So this is the driftwood site here, and we had a drill rig here. Up at the upland site, we had another drill rig going from up here, and we drilled. This is a seismic image of the character of the geological formations here. This purple stuff is the sort of terrace soil that you would think of as being the dirt if you were out there, looking for porcinis or something. You get down below that and you get into the water table is down around here. We're getting down into what we call the 9 mudstone or sandstone formations down here in this yellow. And so that's where the majority of the bore happens, is in this more solid substrate. And this is the driftwood end, and with 2 drilling rigs, we could come from opposite ends and connect in the middle. That turned out to be more challenging than I made it sound right there. Took a few tries before they met up. And we had some challenges because there was some geology that our surveys didn't capture, where things got a little bit loose. They were seams of cobblestone and gravel, and it was a little harder to steer the drill bits in there, a little harder to keep the drilling fluid contained to the bore. And so we had a lot of stops and starts. We started this work in right about the Monday after Thanksgiving, and we just finished it up about a week ago. And so this bore, which was shorter and not undersea, and which we could access both ends of, took us about twice as long as each of the seaward bores. So, you know, every time we thought we were in the clear, we had to shut down and reconsider. This is what the UCMF site looks like. I don't know if any of you remember. It's been a long time ago. There was a Christmas tree farm. Alan and Bonnie Bolt had a Christmas tree farm up off of Wenger Lane. We bought that property and essentially improved. This is the access road. So over here on the right is west. This is an old metal shed building that we took down, but we improved the road. Well, we improved the road, and then we proceeded to tear it up again with all these big heavy trucks. So we'll do that again. Improve the road, improve the grade and the curvature to get these rigs in here, and then graded this area up here, and that's where we started the upland drilling piece of the operation. As you can see, you know, it doesn't ever stay that nice when you start getting into the fall on the Oregon coast. And this was the drilling rig that we started from the upland side, and we made that completion. And then the conduits that we put in here were a poly plastic tube, and they were in a bundle as opposed to one single one. And we had to very carefully guide them into the bore and pull them back down to the driftwood site. And we just made that connection, I think 2 weeks ago today, about 9 p.m. On Thursday, the 3rd of February. Those conduits reached the Driftwood Park. The utility connection monitoring facility, that's the UCMF. We have architect's drawing of that at this point, and like we said, we'll send these out for bid here in a month or so. And so it looks really nice. I'm sure it will look as nice when it gets done. It might not look the same because these are, you know, conceptual drawings. And then the last step is this cable laying operation. And like I said, these are very specialized ships that can carry 4 lengths of cable, each of which are about 12 or 13 miles long. And they lay the cable on the sea floor, and they bury it with a device they call a jet plow. And so as they lay the cable, they're trenching along the sea floor, laying the cable in it, and then burying back over the cable. So the cable itself should be buried 1 or 2 meters deep below the sea floor to the best extent possible. If we run into unanticipated basalt structures or things like that, we'll have to do something different. We typically protect the cable with what they call cement mattresses that will keep it from getting, you know, anchored on or drug up or something like that. And that's all I have. And I know I went fast and gave you a lot of material, and I know it's 1 o'clock. I've got about a half an hour before I need to get to I have a thesis defense to get to this afternoon. So, but I can stay around for questions if folks have them. I'm looking for I don't see any hands up, but let's open up the floor.
So, Georgia.
Yeah, there's been discussion and I missed it, but being a sailor, my concern is, what about naval traffic, both commercial and pleasure?
Yeah, no, that's an excellent point. Part of the siting involved changing the shipping lanes coming into Newport so that the charted shipping lanes now were routed around to the west and north of the site. The other piece of this is that, you know, all of this and everything that we do out there, we work closely with the Coast Guard to get what we call PATON notifications, physical aids to navigation. And they're all required to have a certain amount of lighting and announcement of deployment and recovery and position information. The site itself will have corner markers at each of the four corners of the site. You know, the site is 2 miles in the north to south dimension and 1 mile in the east to west dimension. And so, you know, it's not like there's going to be a set of LED lighted velvet ropes or anything around there, but we will have, you know, lighted navigational buoys there. And the devices themselves, of course, will have, you know, lighting and effectively they'll be on the AIS system. They'll show up as other vessels do on the AIS system.